Yeah, I'm Laura Walizer. I'll be talking about a multi-objective genetic algorithm optimization using multi-fidelity circuit model, which we nicknamed Tomorrow, which makes use of Parsl. I'd like to take a moment to recognize all my colleagues listed here who are also major participants in this work. So the idea is we created this so-called Tomorrow toolkit, multi-fidelity, multi-objective rotorcraft optimization. And as the name suggests, it was created to help analyze rotorcraft. But as we'll talk about later, this could actually be utilized for other optimization problems. As mentioned, we're on supercomputing clusters, aka HPCs or hosts, and the idea is that it builds a surrogate model to predict performance that allows a fast assessment of candidate geometries by the optimizer. And this surrogate model is multi-fidelity, meaning it uses both computationally cheap low fidelity or LF information and computationally expensive but higher quality high fidelity information and combines them. And the surrogate model is also built adaptively, meaning that effort of gathering data is concentrated in the areas of greatest interest. So to carry all this out, we had to make use of a number of different packages. PyMu is the multi-objective optimization package. MuKit does Gaussian process regression. That's what builds our multi-fidelity surrogate model. And of course, the feature today, we use Parsl for parallel workflow management to help us gather the training data that we need. So just real quick, so that we all have a common vocabulary, I want to go over our sort of the hierarchy and terminology we've been using in Tomorrow. Primary process is a PyMu algorithm object. It's basically the type of genetic optimization that we're using. And that's going to contain a problem object that defines the specific problem that we're working on. The problem object will contain a model object. That's our surrogate model. That's mostly the responsibility of MuKit. But these models will own one or more data generator objects. These are what handle the interfacing and running of the actual simulations to gather training data. And there's one for each fidelity level of the model. They're specific to the type of simulations being run. And this is where Parsl comes in. Because each data generator is going to contain a set of Parsl Python apps for pre-processing the simulation, setting up all the input files, substituting the values we want to use, the execution of the actual simulation, and the post-processing, getting the output data back out of the individual data points. There's also a join app to tie those steps together for a specific data point. And then there's an overarching join app that coordinates the parallel execution of a whole batch of points. A particular note, the Python app that we're going to use to execute the simulation, obviously it's probably going to need some particular environment that meets the needs of the simulation program. So it's going to be using a specific Parsl executor. And and considering that they often use very, very different, very different resource requirements between the computationally cheap and computationally expensive simulations, we really appreciate the flexibility that Parsl gives us there. As far as setting up those executors, the main challenge here is that there's going to be some information that's specific to the supercomputing cluster, or host for short, and some information that's going to be specific to simulation programs, and these need to be combined. But of course, since Parsl's Python based, we are able to dynamically build these executors at the beginning of a run and create a proper Parsl config object based on a set of user supplied YAML files that are organized as we've shown at right. There's some directories they called config. In it are some subdirectories, one for each cluster or host. Each one of these is going to contain a host profile YAML that contains all the stuff that's specific to the supercomputing cluster. And there's going to be a subdirectory called executors that's going to have all the stuff that's specific to each simulation program. And this way, all you got to do if you want to run on a new supercomputer or use different simulations is just add or modify files to this file deck, and you'll be able to run without having to modify your main inputs or any of the rest of the code, which really takes advantage of Parsl's separation of code and execution. Our features and early results, just to wrap up, it's flexible. It theoretically accepts any number of input variables, and it can optimize on any number of response or output variables. It can also have an arbitrary number of fidelity levels, although it's most common just to be using two, low fidelity and high fidelity. It's also very modular in design, and this is why it can be potentially applied to other problems, because with the right data generators, this could interface with any kind of simulation program. And here we have results for a relatively simple test problem. This is just an initial test with only a single fidelity level. We changed two aspects of the tip of a rotor blade, and we measured the performance of these tip geometries by looking at the so-called power coefficient. That's a non-dimensional measure of required rotor power. It's a pretty common rotorcraft performance metric. We looked at it both in hover and in forward flight, and our goal was to kind of minimize those combined requirements. And here we can see highlighted in red a set of possibly optimum new blade geometries. And we've been working on validating and generating data for a multi-fidelity case of this same simple problem, but we're very encouraged at how things have gone so far. And with that, I'd like to once again thank my colleagues and thank you all for listening.